Thank you so much I'd like to thank the organizers for inviting me, and this has been just a fantastic conference. I've learned a lot. The talks have been great, and I've had great conversations, so I'm very glad to be here. So I'm going to talk about some various ongoing and future ideas for experiments searching for exotic spin-dependent interactions, which it's great that I followed up some great speakers this morning that have kind of laid the foundation for what I'm going to talk about. So the first topic will be an experiment that I think is almost finished, which is a search for a long-range monopole-dipole interaction, which is very much like what Andrew Gerasi was talking about, but at a different length scale. And then I'm going to talk about the global network of optical magnetometers to search for exotic physics, aka the GNOME, which also has a lot in common with the network of clocks that Andre was talking about. And then finally, a new idea for a possible tool to search for exotic spin-dependent interactions that I'm super excited about, which is this precessing ferromagnetic needle. All right, so first topic is our search for a long-range monopole-dipole interaction. And so this experiment actually has been going on at Cal State East Bay for some time, and we're an undergraduate-only institution. So the first people I have to thank are the many, many fantastic undergraduate students that have gone through the experiment, and I've had it's now over 40 different students work on the experiment over time, and they've all been wonderful and been great. So one thing that I've learned from this experience is, these experiments do take a while. So early on in my experiment, when I thought the result was right around the corner, I brought my daughter to the lab, because she had tiny fingers and could work on electronics and things like that. That was great, crawl into the parts of the experiment that other people couldn't get to.
I heard solder joints.
Oh, pardon? Oh, yeah.
I heard solder joints. Are they cold?
They weren't so good at first, but they're getting much better. And then, so then this summer, I brought her back, and, there she is today. And look, there's two daughters, too, and the students are all different. Yeah, so it takes a while, and that kind of puts it in perspective. But so as Andrew noted, a possible interaction that new types of particles can give, like if there exists some new spin 0 or spin 1 boson, you can get, one of the interactions you can get is this monopole-dipole interaction, right? Now, when I first started this experiment, I was young, as you saw from the picture, I had heard and axions weren't all the rage that they are now, and so I was kind of thinking of this as a new kind of spin-gravity coupling, but it's all the same in the end of the day, the kind of interaction you get. So the Hamiltonian, as Alex noted, you essentially have an effective magnetic field. So in the case of this experiment, the source I'm using, as opposed to Andrew's experiment, is the Earth itself as my source. I was going for the biggest source of monopoles I could find nearby, and here it was right on the floor. So then effectively what you have is an effective magnetic field that's along the direction of the Earth's gravitational field, or the local gravitational field. But so then you've got basically a sigma dot G interaction. So, of course, as already been mentioned, the effect this produces is a shift of the energy levels. Now, these are kind of in some natural units. So if this spin gravity interaction has the same strength as ordinary gravity, or in other words, this would be the idea that instead of gravity being a pure tensor interaction, maybe there is a scalar or vector component that gives these kind of spin couplings. So then K would be 1 in those parameters. So if it had the ordinary strength of gravity. So this would lead to an energy shift about 10 to the minus, a few times 10 to the minus 23 eV. And as we've also seen, these kind of shifts of the Zeeman sublevels give rise to spin precession effects. And the kind of equivalent spin precession you're looking for is on the order of 10 nanohertz, right? So if you put that in terms of a period, that would be, the spins would precess around once every 3 years. So it's not an easy experiment to reach down to that level of sensitivity. So the system we're using in this experiment is a DUAL-ISOTOPE rubidium magnetometer or co-magnetometer. We're measuring simultaneously spin precession in 2 different species. So the special thing about rubidium is it has 2 stable isotopes, very similar in mass, which is nice. And so they have the same electronic structure, but their nuclear structure is very different. And so it turns out, in fact, that the valence proton gives rise to the nuclear spin in both cases. But in one case, the valence proton spin is aligned along the nuclear spin. In the other case, in the other isotope, it's anti-aligned with the nuclear spin. So it turns out if you write down the spin precession frequencies, and you say most of the spin precession is coming from the magnetic interaction, parameterized by your usual gyromagnetic ratio, and then you postulate that there's some new monopole-dipole interaction or a spin-gravity interaction that we'll parameterize by some gyrogravitational ratio, then you can measure these two simultaneously, and by reversing the magnetic field, you can access what's going on. So what we do in the experiment is we take this ratio of the difference over the sum of these two precession frequencies, and then what you find is if you reverse that magnetic field, right, if it was only a magnetic interaction, right, the magnetic field would cancel out. It doesn't care. The precession frequencies, the ratio of precession frequencies, it's not going to matter what the magnetic field is. So you just have this ratio of the gyromagnetic ratios, right? But then if you have this extra non-magnetic precession, it would lead to an extra term in there, right? So then if you take the difference between the magnetic field pointing in along the gravitational field or anti-aligned along the gravitational field, then you get this term that's proportional to this gravitational coupling of the proton spin in particular in this experiment. So to summarize, basically, you take one measurement with the magnetic field and the gravity along the same direction, you anti-align it, you take the difference, 0 if there's no spin-gravity interaction, and if it's not 0, then there is a spin-gravity interaction. So this is a picture of the experimental setup. So the center of the experiment is an alkene-coated vapor cell. So it's a little glass vapor cell, and the inner surface of that cell is coated with a special coating made by our collaborator, Misha Balabas, who he's kind of perfected this coating where the atoms can be spin polarized and bounce off the walls 1,000,000 times. So they have these long spin relaxation times, which give you a very precise measurement. It allows you this long interrogation time that can give you a precise measurement of the spin precession frequency. We apply a magnetic field along this direction with a set of coils, and it's inside a 5-layer magnetic shield. And then we have a shuttered system of circularly polarized pump beams, one for each isotope. And then we have a probe beam that's far detuned from both, so that one probe beam is linearly polarized, and it can read out the spin precession of the atoms contained inside there. OK, so here's a picture of the time domain signals. So we pump them up. We use synchronous optical pumping, I should mention. So the two different pump beams for each of the rubidium isotopes are modulated at the Larmor precession frequency. So they pump them up into this macroscopic spin rotating state, each one pressing at different frequencies. And then it's shuttered, and then we monitor it with the probe, and it decays. So if you take the Fourier transform, you can see that there's two distinct frequencies, one for rubidium-87, one for rubidium-85. Good signal to noise. I was pretty happy. And it's pretty close to the shot noise limit for our measurement. So we can then fit the data, and we get pretty good fits. I'm pretty happy. And we get about, on a single, so each measurement takes about a second. And on a single shot measurement, we get 100 microhertz sensitivity to the spin precession out of, so this is 13 kilohertz. So we have a pretty good fractional sensitivity. So I gave a little, because it's taken a long time, and there are lots of undergraduate students that needed the paper, So we published kind of an intermediate progress report, and some things have been updated since then. So of course, as many people have said many times, of course, if it was that easy, this experiment would have been done back when my daughter was this big. But of course, it's all about the systematic effects. So for example, one interesting systematic effect that we encountered was the following, which was, which seemed like things were getting serious because it was a combination of two errors. So of course, you apply a magnetic field, and the Zeeman sublevels shift. Now, and then that gives us this precession frequency, which we measure. Now, if you turn that magnetic field up larger, right, then you get this nonlinear Zeeman splitting, right, as because you've got the different hyperfine states, and they start to, in perturbation theory, you're crossing over, and you got the bright Rabi diagram. And so effectively what that leads to is a tensor shift. Now, you also get a tensor shift from your probe beam. So you have some your probe light is linearly polarized, and that can also cause light shifts that have that tensor structure as well. So what this does is this is going to shift your frequencies, split your frequencies a little bit. Now, of course, if everything is not so bad because it's a tiny little splitting and smaller than the line width of the line, and so as long as it's symmetric, it wouldn't shift the central frequency. So normally, right, so that's if you're pumping your atoms perpendicular to your magnetic field. But if there's a misalignment, what happens is then you're actually pumping some Zeeman sublevels more strongly than others. You get some spin polarization along the magnetic field, and that's going to shift the frequency a little bit. So that leads to a frequency shift. Now, the good thing, that's a complicated plot. So the good thing is, though, we've got a handle on it, right? Because what you can do is you have some tensor shift, and you have tensor shift coming from two different sources, right? You have a light shift that causes the tensor shift, and you also have the nonlinear Zeeman effect. Now, you need, for a measurement to apply a magnetic field, so you're going to have the nonlinear Zeeman effect there anyways. So all you have to do then is adjust your light shift to cancel out your nonlinear Zeeman effect tensor shift. And you can exaggerate that effect, right, by tilting the direction of the pump to exaggerate that, and then you can measure it easily, and then you can, again, make things as perpendicular as possible and shrink the effect. So that's the strategy there. So this is some data showing this. So this is, we're tuning our probe, we're changing our probe detuning, and we can see that the tensor shift effect is changing, and this is with the magnetic field tilted away. And then you can find this crossing point where you get the cancellation between the tensor shift from the light shift and the tensor shift from the nonlinear Zeeman effect. So there was another systematic effect we discovered. So here's this ratio plotted against the pump modulation frequency. So we're doing the synchronous optical pumping. So it turns out that the Mercury EDM experiment discovered this systematic effect that if there's basically a nuclear magnetic resonance effect. In our case, I guess it's an ESR kind of effect, electron spin resonance effect, where if the modulation frequency isn't precisely tuned to the spin precession frequency, you can actually generate spin polarization along the magnetic field. And so it's a tiny effect. So this is at the 10 to the minus 7 level of the ratio. But nonetheless, that's big on our scale of what we want to measure. And so you can see if you detune the modulation frequency, it shifts around that ratio. So we have to be very careful to tune here. And then if we need to make sure that the magnetic field doesn't drift, so you drift off of that resonance. But that's good. That's why we have a comagnetometer, so we can do a feedback loop, keep the magnetic field constant, and maintain it right there at the correct frequency. And so finally, one of the more recent systematic effects we finally figured out. Well, we knew this existed, but then we didn't know how pernicious it was. Our magnetic field gradient. So it turns out that if you have a magnetic field gradient over your cell, even in this case, it's averaged out pretty well because the atoms bounce around 1,000,000 times between subsequent measurements, and there's this motional averaging. But nonetheless, you get a Berry's phase effect or a geometric phase effect if there's a presence of a magnetic field gradient. And it turns out that every time in our apparatus that you change your magnetic field, actually, the magnetic field gradients change a little bit because of the ferromagnetic, the shields are a soft ferromagnet. So this is very nasty because it also has hysteresis effects. So of course, you measure it, and then you switch it, and then it's different, and then you switch it back in. It doesn't return to its original state. So you're measuring some other systematic effect, and you see a dependence, and then you're confused for a few weeks, and not until finally you figure out, oh, we have to carefully compensate the gradients after every time we change the magnetic field. So then that definitely adds the time the experiment takes. So this plot shows basically, so these dots with the bigger error bars, the shift in this ratio as a function of magnetic field gradient. And this very nice clean measurement here is the width of the rubidium resonance line. So it turns out that magnetic field gradients also broaden the resonances as well as shift the frequencies because of this effect. So we can actually kind of pretty quickly and accurately zero the gradients by scanning through and measuring the width. And so that gives us a kind of an independent check on that that's a little bit faster and more sensitive to this particular effect. So after all these many years, we finally have a preliminary result. So this is this delta R, which is supposed to be 0 if there's no spin gravity coupling and non-zero if there is. And so taking into account all our systematic effects, trying to zero them. So each data point here is about an hour of data, but to get that hour of data takes about 3 to 4 days of zeroing everything and measuring things. So it takes a little bit of time. And so that's our result. Now, but don't get don't get too excited. I don't call Stockholm yet. I mean, hold on, because this is about the range right now of our systematic errors. So this is kind of right in the range of the systematic errors. No, so it's not done yet because I have to, we have a list of other systematic effects to check, including the final systematic check, which is to take everything apart and put in a different cell to make sure it's not anything cell dependent and put it back together. But I think finally we're making good progress, and so this is down at so probably at the 10 to the minus 8 level, and that's probably where it's going to end up. So so this is one of these famous parameter exclusion plots. So this is this coupling strength of the monopole-dipole interaction over different length scales. Here's the astrophysical limits and the existing laboratory limits for the proton. And I should point out too that so we have a bit of a unique niche here is measuring the proton spin. Most of the other experiments have probed either the electron spin, so the University of Washington spin torsion pendulum has looked for electron spin couplings, and then a lot of other experiments have looked for effects with noble gases, which are sensitive to the neutron spin. But it turns out, like for example, the KSVZ axion, the kind of standard axion model has the coupling to the proton is predicted to be 100 times bigger than the coupling to the neutron. So it's very plausible that you could have very different couplings for the two, so to treat them as independent things. And so it looks like with that present sensitivity, our limit's going to improve on the current laboratory limits by a factor of 4 orders of magnitude, and getting close to the astrophysical limits. And I should point out too, if you dig deep down into the astrophysical limits, they're somewhat model dependent. So they don't totally exclude all kinds of monopole-dipole interactions, but a certain subclass of them. So, all right. So next topic, moving on to new and other things, is the gnome. So the idea, as Andre explained so beautifully earlier, is that okay, so we're in our laboratory. We've been searching for 10 years for this kind of constant offset effect in our spin precession. But every once in a while, all of a sudden, there's a spike or a transient event, and hey, does that mean anything? Or maybe it was just nothing. So we can't really, with one single sensor, do a very confidently distinguish some transient event from random noise. But if we do have a global array of such instruments, there's tools that we can use to confidently distinguish such transient events. So we wrote a proposal here. So one of the things, and this proposal talks about looking for these topological defects, these ALP domain walls with one of these kind of spin-dependent couplings. So it's kind of already been explained, right? Is that these axions form? There's some symmetry breaking scale that happens, and it has this kind of sombrero-like potential, just like the Higgs interaction. And then once there's some other interaction turns on, then you can get these kind of different local minima, these different vacuum potentials for your axion field. And what you can have happen, depending on whether or not this symmetry breaking and interaction turns on, these scales happen before or after inflation, you can potentially end up with topological defects if this happens after inflation rather than before inflation. In this case, one thing that can form these domain walls, and actually early on, right, these domain walls are so are such a natural consequence of the axion physics. Is this was a reason like, whoa, so this axion couldn't be true because there'd be so many domain walls everywhere, the universe would collapse, right? But it turns out that if you use other things rather than the QCD axion, but some of these axion-like particles, it kind of frees up the parameter space, and it seems like it's a plausible thing. So, okay, so if you're going to look for such things, so for the axion, so anytime you cross over from one region where the axion has a certain value to another region where the axion has a different value, you pass through one of these domain walls, and you have one of these gradient spin couplings that Alex talked about, kind of like the axion wind kind of coupling. So, all right, if we're going to, and as I've already been pointed out, you're traveling through this sort of this virial velocity with respect to objects in the galaxy is about 1,000th the speed of light. So if you're going to conduct an experiment on a reasonable timescale, let's say, and get a couple events so you can verify that you're looking for something, you say, well, okay, well, it's not only is it, this is the experimentally accessible, convenient region, but it's also at least plausible that would be kind of the spacing of these kind of things would be 10 to the minus 4 of a light year. So you get about 10 events a year, right? So the characteristic wall thickness is also given by, basically the Compton wavelength of the axion particle. And so this kind of determines what kind of mass you're sensitive to in terms of this wall thickness. So that means if you cross through one of these walls, you have a duration of this signal that's going to be a millisecond, and if you go to smaller masses, are somewhat longer than a millisecond, right, depending on what your mass range is. So the idea is, in this model where the mass energy that's associated with dark matter is all stored in the domain wall, and so that kind of determines, and that in this tension in the domain wall, and so that determines from the dark matter density basically how big your signal is going to be. This A naught is the amplitude of that axion field. So so if you assume all the dark matter is in these domain walls, then you can get a predicted amplitude. So there's actually, so the Hamiltonian that, for example, Alex mentioned is this Hamiltonian is coupling to the gradient of the spin. It turns out there's also a quadratic coupling you could have as well, which would be a coupling to the square of the axion, the gradient of the square of the axion field. And it turns out that the present limits on the quadratic coupling are much weaker than those of the linear coupling. So that's, I don't know, something to think about for other experiments as well. So we also published kind of a progress report on this experiment. So presently, the GNOME experiment today, actually, now we've got quite a big collaboration. In fact, in terms of the experiment, the management issues are almost as complicated as the actual, probably more complicated than the actual experiments themselves. So Dima and Holger both are participating at Berkeley. I'm at Cal State East Bay. Paul Hamilton at UCLA is participating, and Jason Stonecker from Oberlin College is participating. We've got Szymek Pustelny at Jagiellonian University, Antoine Weiss at Freiburg University, Dima Buder's also in Mainz. We've got Ron Fullman from Ben Gurion University, and we've got Hong Guo from Peking University, and Zhengten Liu, who's now at Hefei in China, and finally Janis Mertzis and Yun Shen over at KAIST. So anyways, so we've got, so it makes these, we have a weekly meeting, and I have to get up really early in the morning, and then they're up really late at night, and it's very exciting. And we also have a lot of people working on both hardware development for the sensors. Tom Kornak at Twinleaf, Sam Affik at Mainz has worked really hard on the software development and data analysis. So we're collaborating with especially Chris and Josh from the LIGO collaboration. So as you can imagine, the kind of data analysis we're doing for this kind of network search is very similar to the kind of things that they do in LIGO. And so we're actually using the same exact data analysis tools that LIGO uses. And Maxime is the one who helped us with that original proposal. So actually, we just recently had a data analysis boot camp at Northwestern University, where we went through, and first we analyzed gravitational wave data and found the gravitational wave ourselves, and then we started changing the code so then we could look through the GNOME data for transient events. So we've developed, as I think was mentioned before, for $3,000 or something like that, you can buy from Szymek, has built this GPS discipline data acquisition system that the different groups are using. There it is, the box, all taken apart. We have a software that you can plug into then that takes the data and then puts it in the right format for everything. And we have a software program now that uploads it to a server in Germany that collects all the data from the different stations. So then you can and organize it so we can analyze it. So we've done a couple trial runs, and our most recent trial run was this July. So here's some data, some magnetometer data from Berkeley. As you can see, we're running into domain walls all the time. Blam, 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 blam. Right? So this shows the data for about 24 hours. And so what this is what we call a whitened spectrogram. So we can look at this data both in time domain and the frequency domain. And you can see that these different spikes show up, and they have some particular frequency characteristics, as well as particular times that they show up there in that Berkeley data. Oh, okay. But then, of course, Berkeley had a second magnetometer running at the same time, which did not see anything. So, so this immediately shows the value of having two sensors, right? So one sensor is seeing domain walls all the time, or something all the time, and the other guy is not, therefore ruling out the first guy. So that's cool. So here's the sensor in Switzerland. Okay, very quiet. here's our magnetometer in Hayward, also very quiet. Oh, look at what happened in Poland. Man, something cool happened. You know, maybe we had like a real, but luckily that was also ruled out by the other experiments. Yeah. Oh, yeah. You should. Oh, let's see. Oh, yeah. You can see in the Hayward. It's maybe a little hard to see, but there's a kind of a line there which shows up at 60 hertz, so you can see 60 hertz noise. It's very faint, but if you look closely. Let's see. Oh, here we go, and here's Germany. Definitely a couple events there, which show up very loud in our spectrogram. Anyways, so we haven't completed this analysis for the latest one. We're still working on that. But then what you can do is actually the question came up. Jerry was asking, okay, what about systematic? So in the GNOME experiment, the way we do that, which is the same way they do it in these LIGO sort of searches for unconstrained random things, is so what they do is you can time shift the data. So basically say, all right, if one of these events passes through your network of sensors, right, there's going to be this particular timing event, right? So you can take your data, so even for one individual sensor, you take your data, you shift it by 10 hours, right? So there's no way that it's going to take 10 hours for this thing to get through the Earth, right? And then you overlap the data, and you see how often do you see coincidences, right? And so that gives you your background rate. So essentially that kind of, in a sense, covers both your systematic and your statistical uncertainty, because you're saying, well, how many random times do I have coincidences? And that's kind of a background rate. So that's how you calculate this sort of background rate. And then you go back to the time overlap that you think is reasonable for a real event, and you see if you see an excess of events or an excess power of that event, even for a single event, if it's way above your background floor, then that's something significant, right? And that's basically how LIGO does it as well for these coincidence searches. I feel like I was going to say something else. Oh, yeah, and the other thing we do have too, right, is we're developing VTOs for each sensor, right? So you have you can get a nice accelerometer and gyroscope and magnetometer to put outside your shielded sensor. So if somebody kicks the table or drops a magnet, like it probably happened, there, right? There's a red flag that goes off in the data stream that says it flags that data as like, oh, ignore that, right? So then we can have extra VTOs of our data. Yeah, this didn't really show up too well. But so the exciting thing is, so for the existing GNOME, the one we've got set up that we did the practice run for, if you look at that quadratic interaction, so for the quadratic interaction, the astrophysical constraints constrain this coupling parameter, which is in units of GeV, that it has to be larger than 10 to the 4 GeV. That's what the astrophysical constraints say so far. But so just for our present run, if we run for a few months, with this assumption that of the wall spacing, we'd be sensitive to this region of parameter space, which is presently unconstrained. So again, I think the point that Andre made is, and others have made, right, the whole name of the game is there's a lot we don't know. This could be the dark matter. There's many other possibilities what it could be. But at least we're looking somewhere where we haven't looked before. Right? I think that's the important point. So we're looking for in some unconstrained regions. So that's pretty exciting. So I think we're going to push forward and try to get search this parameter space, see if we see anything over a longer science run very soon. So the next generation that we're already trying to work on is, so right now we're using magnetometers. I think I didn't really explain this too well, but very similar to the one I was using for the spin gravity interaction search. So they're basically those kind of magnetometers, just spin precession magnetometers looking at alkali spin precession. But it turns out that there's has been developed a very sensitive magnetometer that's essentially we're looking for couplings to helium-3. So kind of like what Andrew was looking for. And it turns out that this has much greater potential sensitivity. So if you look at, if we convert to, and these are these SURF comagnetometers, these spin exchange relaxation-free magnetometers were developed by Mike Romalis and his collaborators at Princeton, and Tom Kornack, who's working with us, is helping us develop those, and that was his big thesis project. So it turns out that in this case, you can reach a much bigger range of parameter space to this quadratic coupling. And also I should note, too, that the sensors we have now are sensitive to electron and proton couplings, and our new, this SURF comagnetometer would be primarily sensitive to neutron couplings. So even among the GNOME sensors, you're kind of sensitive to different portals, as you'd say. And so here, for that linear coupling, which is kind of the more traditional coupling you look for axions, we'd get this sensitivity over a big mass range, 4 orders of magnitude beyond the astrophysical limits, which are shown here at the bottom. So pretty exciting. So this was something that I was just thinking about the last couple days and on the airplane, so it's a little preliminary. But you can also imagine that you have some clumping of dark matter, right? So again, like you're going through some cloud. So it'd be like basically the axion wind kind of experiment, but instead of being it uniformly distributed, maybe it clumps up a little bit. So again, what we need is for the mean free path to not be too long, right? So that we'll run into it every once in a while. And so our bandwidth of the GNOME sensors is about 100 hertz. So this kind of restricts what kind of masses we'd be sensitive to, because this would be the Compton frequency that we could probe. So I was kind of wading through the literature, and so we saw, you can see that it's plausible that these things would be on this kind of on the size, kind of the minimum size would be like the de Broglie wavelength, maybe a little bigger, a little smaller, depending on if it's gravitational clumping or other things. And you get the signal duration, da-da-da-da would go, and you can go through the little back of the envelope calculation, and you can see that the present GNOME actually is sensitive to these kind of things and could search for these clumps of dark matter, and the future GNOME could be even more sensitive. Okay, in my remaining 5 to 7 minutes, I will tell you now about this last idea, which is this precessing ferromagnetic needle. So this is something that Alex and I and Dima worked on for over a year, and it was so exciting. I mean, it was an emotional roller coaster. So we were on the phone with each other, like twice a week. It was so much fun. But then sometimes it seemed like it would be the greatest thing ever, and other times it seemed like it wouldn't work at all. But at the end, it kind of settled down, and it looks like it might work. So all right. So far we've been talking about these spin precession magnetometers, where you're measuring basically Larmor precession of atomic spins. And how do they work? Well, basically, right, you're measuring a precession angle phi, which is the Larmor frequency times some amount of time. And the way you measure that is you're reading out this, you polarize your spins along one direction, along x. Let's say you have n spins all polarized along x. And if they precess by a small angle, then you get a little projection along y. And that tells you what your angle is, how much is precessed. And from that, you can read out what the magnetic field is. Now, if you have n of these spins, the standard quantum limit is going to be given by the relaxation time times the duration of your measurement over the number of spins, and take the square root, and that gives you how precisely you can measure it. And where does that come from? It comes from the fact that this is going to be a random walk in this precession angle with step size 1 over square root of n. And that's given, and you have basically gamma relaxation times the time number of steps. And that's just simply because of the quantum uncertainty in the spin projection. But so we were thinking along. Back when I was a young Boy Scout and I was out in the woods, I'd take my compass to try to find where I was going, and then the needle would always orient towards north, and I could get my way out from the woods. But then my whole career as an experimentalist, I was watching these spins precess around the direction of the magnetic field, and so I thought to myself, and when I talked with Alex and Dima about this question, and we were like, hey, why is it that your ferromagnetic needle always just points towards north, but your electron and nuclear spins precess around the north? I mean, that's very different behavior. And so here's your spins. So they're acting like gyroscopes, right? But your magnetic needle doesn't. So why is that? Well, so it's pretty clear after some discussion that there's two regimes, right? So, and it's just like when you spin a top. So if you take a top and you spin it, right? So at first, if you have enough spin angular momentum around the axis, right? So if that's much larger than the kind of rotational angular momentum or orbital angular momentum associated with the tipping over of the top, right? Then it's going to wobble and precess, right? But if you go to the opposite regime, where there's more angular momentum from the tipping than the spin, it's going to tip over, right? So there's a tipping regime and a precessing regime. It just depends on the ratio of that.
It's not spin here.
Yeah, so this would be the. So for a top, it would be the spinning motion. So how much angular momentum is associated with the spinning motion around the axis? Yeah, so you spin it up, right? And then the tipping would be, if you let it tipped over, what's the angular momentum associated, with that falling motion?
I see.
So in this case, so in the case of a ferromagnetic particle, right, this condition is saying that now your spin is being provided by intrinsic spin instead of, like for a top, this spinning around the axis. And so we want that the n times h bar, that spin, intrinsic spin along the axis, is much greater than the moment of inertia times the Larmor precession frequency. Right? So as long as you're in that regime, you're going to precess, right? Because the amount of angular momentum you're adding to the system is small compared to the vector of angular momentum along the axis. Okay, so this leads to a condition then that says, all right, so what you have to have is you're limited by kind of a threshold precession frequency or a threshold magnetic field to maintain that condition. So you have to go to a situation where nh bar over the moment of inertia of your object is much, much greater than the spin precession frequency. So it turns out that, so could you get a ferromagnetic needle to actually precess instead of line up along north? And the answer is actually, at least we predict that you totally could do this. Because, so let's say you take a needle that you want to get a small moment of inertia. That'll help you out. So you go to a small needle about 10 microns long and about 1 micron in diameter. And so in that case, the threshold precession frequency is about 100 inverse seconds. And the threshold magnetic field there is about 10 microgauss, which we can easily achieve in the laboratory. So the prediction is, if you put it in that put a ferromagnetic needle in that kind of environment, it'll precess around the axis. So then we asked the next question, was, well, how would a measurement work if we tried to measure a magnetic field using this technique? So let's say we put a squid, a state-of-the-art squid, right up close to one of these needles and watch it precess around. Well, we put in the back of the envelope numbers, and we nearly fell over. We went crazy with excitement. The predicted sensitivity is 10 to the minus 16 Gauss, and it averages down as t to the minus 3/2. It's too good to be true. In fact, that was our next thought. Wait, that's too good to be true. Because let's say that you had the perfect system of spins. You had no relaxation of your spins, and so you'd set gamma relaxation equal to 0. What's the kind of sensitivity you could get based on the standard quantum limit? Well, that would be 10 to the minus 13 Gauss, and it would average as the inverse power of time. So wait a minute. This needle is crushing the standard quantum limit. That doesn't seem possible. Well, but then we thought some more. So, okay, where is the standard quantum limit coming from? Again, as we said, it's a random walk in the precession angle. But, of course, you could always average your measurements, right? And so, so it's this random walk is 1 over square root of n. But of course, if you average n sub m times, you reduce that uncertainty by a factor of 1 over square root of n to the m. So in the needle, you've got this mesoscopic system where you actually have very rapid averaging because of the spin lattice interaction, right? But this is a strange, unique system because normally that quantum interaction that kind of averages your quantum uncertainty and gives you kind of classical behavior, usually that causes a random walk of the variable that you're trying to measure. But in this case, because of the gyroscopic stability, because of conservation of angular momentum, it doesn't undergo a random walk. It undergoes random, rapid fluctuations about a mean. So in that case, there's no random walk in phi, so you don't get the same kind of behavior of the uncertainty that you'd get for a gas of spins.
I didn't understand. Why does the needle not behave as one object with a certain spin and a certain
It does, but it's tied to the lattice. So the key in the case of the needle, as opposed to a gas of atoms with no relaxation, is the spins are all tied to one another, and they're also tied, and they're kept correlated. They're completely correlated by the interaction with the lattice, right? And so then the lattice is in the kind of the spin phonon coupling and so forth, and is keeping them. They're constantly fluctuating around the mean, but lined up. So that's the kind of the difference.
If I take the macroscopic spin of the needle at moment inertia and so calculate the standard quantum limit, then you say I got something that's way too big.
Mm-hmm.
So it does not behave like one object with a spin at the moment of inertia.
So that standard quantum limit would be forgetting about the moment of inertia, I guess. Yeah, so that standard quantum limit would be saying that you just have n independent spins and no relaxation. So, and you measure the quantum limit, and that's what you get. So the key, so I mean, you can't get this without the lattice interaction. So that actually ends up being key to the weird behavior of the needle. So they say the two things that are necessary for this crazy behavior is the lattice being there to interact, kind of as a thermal bath that's causing the rapid spin fluctuations, and then the ferromagnetic interaction that keeps it aligned. So another way to think about this is, okay, all those quantum fluctuations, of course, quantum mechanics is right, so all those quantum fluctuations are still there, but they're spread over a huge bandwidth, right? So by integrating, you basically act as a low-pass filter on those quantum fluctuations, where normally you don't get that if your spins are undisturbed. So if you then plug in the numbers, here's your standard quantum limit for zero relaxation, but here's the sensitivity of this needle to these to spin to a magnetic field in principle. So here it's limited by the detector sensitivity of the squid, and here it actually is limited by gas collisions, if you consider these kind of things. And ultimately, this is kind of the ultimate quantum limit if somehow magically you have vacuum beyond what you could get in some sort of superdetector. All right, so these are kind of some of the things we considered. There's one big problem, sometimes referred to as the MC Hammer problem, because you can't touch this. Any coupling of this ferromagnetic needle to the environment is going to really disturb the sensitivity because it got way too sensitive, right? So so this is the problem. So how do you float this thing? Well, of course, we can go into space, but as we've heard, going into space is expensive. So so the question is how we can do this in the laboratory. So we're still working on this. So if anybody has any ideas, that's good. Okay, so I think I am now definitely at my time limit. So I will close with that. And thanks very much for your attention.
Any questions? So basically what you're saying, I'm sorry, I'm only half serious, but what you're saying is that that you use basically rather than quantum entanglement, kind of classical entanglement to get below the standard quantum limit.
Basically, that's right. Oh, sure, yeah.
So what's setting the limit of delta BQ there?
Oh, so that's a good question. Delta BQ. Oh, okay. So that. Oh, I'm sorry. Yeah. So that limit is actually, this is delta BQ. Sorry. So this is from, if you go back to ultimately, okay, so what's actually determining the noise in the needle? So if you had some super idealized measurement scheme, so not an actual squid, but some squid of the future, right? Then ultimately the intrinsic noise of the system is due to the fluctuation dissipation theorem, right? So that's what determines that ultimate quantum limit of the needle, which to me I think is also quite significant, right? Because right now, okay, so I mean the whole thing's completely insane, but all right, so right now it goes so far past the many orders of magnitude past, just with sort of like the available technology, it would go potentially, if you could solve some of these other problems, it would go so far past the existing spin precession measurements. But also the fundamental noise limit intrinsic to the needle is well below that as well. So that these are technical noise limits, but there's also a fundamental limit that's insanely small. So if indeed this is true, it's got growth potential, long term, I would say. So anyways, so that's it. Yeah. Oh.
Sorry. So I think it sounds really awesome, but could you just walk me through the sequence? And if I want to do, I had a single spin, I imagine I cool it down, it's polarized, I give it a pi over 2 pulse, and I listen. Is that what you're doing here? Is there a pi over 2 pulse?
You do have to. Okay, so I would say, so the actual experiment, right? You'd have to, get your spins lined up in zero magnetic field or whatever, get your needle lined up, your position, right? And then you got to non-adiabatically turn on some tiny field, right? And then because you don't want it to kind of adiabatically follow the field, right, to get it to precise. So you turn that on somewhat suddenly, and then watch the thing go.
So in NMR, you usually don't change the field. You give it a pi over 2, but here you change the field, and that's what you see. Okay.
Right. Yeah. We talked about because we did have some conversation about this. Could you do NMR kind of characteristics? And that's complicated because of the spin lattice interaction. So So I mean that requires. I mean we thought about it, but it didn't seem too promising. Because if you go into the rotating frame, it doesn't work the same way as it would normally. It got problematic. But so instead of a pi over 2 pulse, I'd say a sudden field turn on would be preferable. Or you could move a little sensor or move a little mass source next to it, in and out, non-adiabatically look for those kind of effects.
All right. So since I cut everybody off after that time, I will do that as well, especially since people might be hungry. So first, let's thank Derek.